Okay, hi everyone. My name is Clive. I am a PhD student down at CQT, and I'm part of the Valerius-Guarani group, which is a theorist group. And my research angle is towards quantum thermodynamics. And this little thing that I'm doing right now is an introduction that I have to append to a lecture recording of this QCamp lecture that I did on qubits and superposition. I mean, you definitely already can see that from title screen and from clicking on this video. And this particular lecture was a significant one, at least in terms of its placement in the camp, because it's a kind of a bridge between the first day where we talked about a lot of math, theoretic stuff, mathematical objects and certain rules of how the mathematical manipulation happened, mainly in terms of linear algebra, in terms of eigenvectors and eigenvalues, things like that. Before we go into the more applied physics side of things, where we talk about optics and talk about spin and stuff like that, and cryptography and stuff like that. So we were in a kind of a in-between moment, a kind of in-between space, where while we were trying to bridge over from all these math theoretic stuff over to the actual physical system. And so we were in a kind of this liminal situation whereby we're talking about theory and concept. And for many of the students at the time, we were kind of touching on quantum theory proper for the first time. Yeah. So I thought that a good way to kind of start this out is to just acknowledge the fact that when people think of quantum theory and quantum mechanics, many different things come up, right? Okay, there's a slew of quantum mechanics is almost too convenient and too mysterious a tool not to use in narrative. It is something that can be exploited because of how spooky it can seem, or how mysterious. And so it has been used to justify time traveling in certain movies. Is people speak of a quantum realm that you can travel to. So obviously, when we have these things out in the open, some of us might already have this inkling that like probably the quantum theory there is not exactly accurate. But nevertheless, these are the kind of things that, unless we have a kind of study it formally, these are the things that, like it or not, is going to be at the back of your, at the background at least. Okay, and so with that in mind, it means that we have our work cut out for us. Okay, so at this point, I'll transit over to the lecture itself, whereby I talk about the approach that I would take for this lecture. So my approach is that because it's our first formal lecture about quantum mechanics, in light of how there's oversimplification and downright fiction and sometimes just misinformation, we'll need to have both technical and conceptual clarifications. And so there'll be a bit of math, and there'll also be some conceptual understanding stuff. Okay. So let me just be very straightforward with you guys. This is what I hope you guys will take away from the lecture. Okay. The first thing is that you will understand what a qubit is. And secondly, what it roughly means to say that something is in a superposition, at least with regard to qubits. Next thing is that I will be going through this very important foundational principle in quantum mechanics called the Born rule, and which deals with how systems are measured. And then the last thing is, again, first intuitions about these things called quantum operators, okay, which have to do with what it means to act, the kind of theoretic structure behind acting on a quantum system. Okay, so this measurement and this is evolution or the acting of things. Okay, so this is how I'm going to outline my the lecture. And so if you guys are like writing notes, this is roughly how I'm going to go through the thing. Okay, just to take note of some stuff. Okay, I'll be sticking to pure qubits and single party qubits. Okay, so what does that mean? This is quite theoretical, but let me just say that for pure qubits, it's something that's perfectly constructed and perfectly known. So it's basically nature's most accurate version of the thing. Okay, so we'll be dealing with pure qubits. No like quote unquote classical uncertainty about it. As for single party, it just means that there's just one isolated system. And later on, I think Bengi will be going through more multiple qubit scenarios whereby you can see entanglement and stuff like that. Another thing to kind of say, probably a needless disclaimer, is that the kind of language that I'll be using here will be conforming to what is sometimes called a textbook interpretation of quantum mechanics, and often more often called the Copenhagen interpretation. But I'll be kind of following this kind of typical language. And of course, there are other interpretations available, and we can talk about it. But the reason why I've chosen to talk like this is because it's just pedagogically, teaching-wise, is the most tested, and that this tends to be the most operational choice. When it comes to be in the lab, when they talk about these things, they'll use the same kind of language. Okay, all right, so let me just move on. Okay, so as promised, the first thing I'll do is introduce the qubit, and this has to do with talking about, I'm just gonna lay out like why the qubit is such an important thing to talk about. Okay, so what's the qubit? The qubit stands in for the term quantum bit. Okay, and it basically represents a quantum system with a 2-level degree of freedom. Okay, what on earth does that mean? Hopefully through examples, you guys will get a sensing on what that means. But just remember that the 2-level part is what makes it a qubit. Okay, and so there are 3 main reasons why looking into the qubit is such an important thing. Okay, the first reason is, as I alluded to, qubits are a class of quantum systems that represent many different physical things. Okay, so qubits are kind of like a category, like 4-wheel drive or something like that. And there are many different sort of 4-wheel drives that would conform to this. Okay, so don't think of like, when I say qubit, don't think of a specific physical system, okay, unless I say so, right? So unless I say so, this can refer to all these different classes. Okay, and this would make it how to say, very context sensitive when we talk about qubits. Okay, so some examples of qubits, something that Alex has already mentioned yesterday, was the spin particles, namely the spin half particles, which have a qubit degree of freedom with regard to their magnetic moment. Intrinsic magnetic moment, that is. Okay, so polarization of photons is a very different degree of freedom from magnetic moment. Okay, and by the way, photons are not spin half, they spin 1. Okay, so but polarization, on the other hand, of these photons are a qubit degree of freedom. Even the paths of an interferometer, okay, this is something that you guys will meet later on with Lynn's lecture. Okay, is also a qubit, a kind of degree of freedom. And very important in quantum computing, this very clever way of building a kind of a circuit that mimics a kind of harmonic oscillator, and then they amend it such that you can truncate the first 2 energy levels, the ground state and the first energy state, such that it's effectively a 2-level system, and that's how they make it a qubit inside the quantum computer. Okay, there are other sorts of qubits that we will touch on later, but the point here is to say that notice that the qubit represents many different physical things. And so therefore, the 2 levels are always context sensitive. You need to know what physical thing you're talking about. And the operators, even though mathematically they may be the same, physically speaking, a mathematical operator for a magnetic moment and a polarization is going to be very different, right? Okay, and so that's it. The math, on the other hand, is completely the same. Okay, the math theoretic structure is going to be same for all qubits, which is very nice. Okay, and so it's in this lecture that I'm going to focus on this math theoretic structure. And so what this means is that understanding this math theoretic structure underneath the qubit, right, will help you understand all these physical systems in a deep way. Okay, and so that's why it's so important to look into these things. Okay, next. Okay, because we're CQT and QT stands for quantum technologies, it's important to know that qubits are the cornerstone of quantum information and quantum communication and computation. Okay, and this is unsurprisingly because of the very kindred connection it has to the classical bit. All the way that we are communicating through Zoom right now, the way that your folders in your computer all the memes in your computer are being encoded to your memory is all by these classical bits, right? And so the quantum kind of brother of the classical bit is the qubit. It's also a 2-level system. And because of this connection, it is also the cornerstone to quantum information, quantum communication, and quantum computation. Okay, if you're interested in this kind of more information theoretic stuff with regard to the classical bit, you can go and look up this thing called Shannon information, and also this other thing called noiseless coding theorem. It's quite interesting. Okay, but the point here is that qubits are indispensable. If you want to know quantum technology, like it or not, you need to have a very good understanding of qubits. It's very, very important. Okay, and finally, for those of y'all who are a little bit more foundations minded or something, you can also notice that qubits help illuminate very counterintuitive ideas in quantum theory. And why they help you illuminate it is because the qubit is the most simplest quantum system. And so what you are showing is this very strange character of the quantum theory. but it's in its most distilled form. And you will find that even with regard to a single qubit, okay, you can already notice some very, very strange, very different from classical mechanics situations going on here. Okay, so and these notions can then be recontextualized to more advanced situations. By the way, in the more advanced situations, quantum mechanics only gets weirder. Yeah, but if you want to have the very bare bones of these strange notions, then you will need to look at looking at qubits will help you show it in the most obvious form, the most distilled form. All right. Okay, so then these are the basic reasons why I think it's really important for us to look into qubits. Okay, so this is just me introducing the qubit. Okay, now we go into the deeper, slightly more technical stuff. Okay, understanding the qubit. All right, so the two levels of these qubits. Remember, we are kind of releasing ourselves from the physical context. We are just looking at the math theoretic structure. So the qubits are defined as a quantum system with a two-level degree of freedom. Okay. One thing that's very important in quantum mechanics is actually the notion of measurement. Okay, so let me just say that what these two levels corresponds to, okay, depends not only on the physical system that we're talking about. The magnetic spin of something is very different from a polarization of something. Okay, but also on the measurement basis that we're using. So the basis, every time we are talking about quantum mechanics, right, you constantly notice us talking about measurement basis, which basis do you use or whatever. Of course, this is fundamental to quantum theory. Okay, and so for starters, I'm just going to introduce one computational basis, the most basic of them all, which is the computational basis, which can be represented as such. Okay, so if you kind of connect it to a vector representation, we can just put for the 0 ket, okay, I'm going to call this a 0 ket, it's going to be 1 0, and then for the 1 ket, it will be 0 1. Okay, nothing particularly interesting is happening here because we're sticking to the very bare minimum for now. Okay, this is, to the surprise of nobody, this is orthonormal. It's orthonormal basis. Okay, so let me just kind of say something that is almost too obvious to say, but I need to say it anyway. Okay, so if my quantum system is in a 0 state and I'm measuring it on the computational basis 0 1, okay, I will always get a 0 result. Okay, meanwhile, if my quantum system is in a 1 state, okay, and I measure it in the computational basis 0 1, I will always get a 1 result. Okay, that is just axiomatically the case, right? It's just trivially the case. Okay, and so at this point, some of you might be wondering, like, hey, what's the big difference between a classical bit and a qubit? Because in a qubit situation, in a classical bit situation, we have the exact same thing. Okay, and that's where the notion of superposition comes kind of roaring in. Okay, so let me just introduce to you guys two very important superpositions. Okay, there are much more other superpositions which we'll touch on later, but here we'll look at the two very important ones. And this is called the plus, what we can call the plus ket and the minus ket. Okay. So the plus ket is basically this, and there's this square root 2 thing, and then after that there's this minus ket. Okay. And if you want to use the kind of vector representation that we have been using so far, it will look like this. Okay, so in this situation, we have a sort of different scenario. Okay, if my quantum system is in a plus state and I measure it along the computational basis, very important that I'm measuring it along the computational basis here. Okay, the 0 1 basis. Okay, then half of the time I'm going to get 0, and half of the time I'm going to get 1. Okay. Likewise, for the 0 1, for the minus state, the same thing applies. Okay, the statistics for the plus and the minus thing is actually virtually the same. Okay, the differences only come when you're measuring it in a different basis. Okay, but for the computational basis, it's exactly the same, the statistics. Okay, so more on what these probabilities mean later on when we touch on the Bond rule. But for now, okay, now that I've introduced this to you, let me kind of take a detour and we're going to talk a little bit about what superposition is and is not. Okay, so I hope everyone's following so far. Okay, so the first thing is that now that I've described this plus and minus state, and then one of them is 50, when you kind of measure it in the computational basis, half the time I get 0, half the time I get 1. So that sounds a lot like a coin toss, right? Half the times I get hits, half the times I get tails. Okay, so then the question is, okay, so are superpositions basically coin tosses? Why even come up with such a cheap name when ultimately we're just dealing with the typical kind of gambling situation? Okay, And the answer you might expect is that no, these are not the same thing. And the differences, at least according to standard quantum theory, is that according to the classical coin toss, if I had all the information that nature could give about the classical coin toss, I can actually predict it. Okay, if I was a really, really smart guy with a supercomputer. Okay, if I had all the initial conditions that nature could offer me, I have all the degrees of freedom with regard to the environment and how whatever the kind of energy that was put into the coin while it's being tossed and whatnot, I can actually predict whether it's going to be heads or tails before it hits. Okay, that is according to classical mechanics. This is the case. If nature gave me all the information, bam, I have it. I can win every single coin toss gamble that I want if I have the proper computer to compute that kind of stuff. Okay, and so this kind of randomness that when you flip the coin and we think that it's random is this kind of randomness from ignorance. It's not genuine kind of randomness. Meanwhile, for quantum superpositions, according to quantum theory, is that even if nature told you every single thing that was possible about the superposition, right? If you're measuring a plus state in the 0-1 basis, like it or not, you're going to not be able to predict whether it's going to be 0 or 1 ultimately. And so this is a very different kind of randomness, which is intrinsically random. Okay, you cannot forecast the result beforehand, no matter how much information you have about nature. Okay, so this is actually what the Schrodinger's cat, a thought experiment, was supposed to was trying to put out before it was taken over by, I don't know, Rick and Morty and changed into a completely different thing lah. Okay, but so Alex actually kind of mentioned this, but let me kind of go through this very familiar thought experiment with you so that you kind of get what Schrodinger is saying in a deeper way. Okay, so this is a version of the thing that is more related to what we're talking about here about qubits. Okay, so in an isolated environment, okay, I have a qubit. Okay, let's say a qubit in a plus state. Okay, and this qubit is connected to a measurement device, which kind of dispenses different things depending on what it measures. Okay, and so if it measures 0, it's gonna dispense a delicious treat. Meanwhile, if it measures 1, it's gonna release a poisonous gas. Okay, and there's a cat inside this isolated environment with this device and the qubit. And depending on what it gets, if it gets a treat, then it stays alive. It's very happy, right? Okay, and if it gets the poisonous gas, then it's dead. Okay, so the important thing is to note that this then results in a quantum superposition, of this cat being alive and the cat being dead lah. Okay, so why did Schrodinger kind of point this out? Okay, he's obviously not trying to say that you see, when you open up the box, right, you will find out whether the cat was dead all along or alive all along. That would be the scenario with the coin toss. So if you have a very different situation where you put like Harvey Dent in an isolated environment and he has his fix, and so he flips a coin to decide whether to kill the cat or not. Okay, and maybe he kills the cat the moment he gets into kills or leaves the cat alone the moment he gets into the isolated environment. And one day later, when you open up, you will just find out whether the cat was dead all along or the cat was alive all along. Okay, so it's a kind of what this is called an exclusive OR. It's either dead or alive. Okay, all along. Meanwhile, for quantum superposition, you have a very different scenario. You don't have you find out whether the cat was dead all along or alive all along. Rather, when it was in an isolated environment, it was in a quantum superposition of being dead and alive. Okay, which is this intrinsic randomness thing that was going on. Okay, so clearly Schrodinger didn't come up with a thought experiment to say that when we open a box, we find out what has always been the case. Rather, he was saying that via quantum theory, we have this ridiculous thing. And the ridiculous thing is this, that we have a cat that's in a superposition of being dead and alive. That's ridiculous. Okay, ascribing the terms dead and alive, the properties dead and alive to the cat in the same sense and at the same time, right, is very counterintuitive, if not completely absurd. So Schrodinger was trying to say that, hey guys, something's off. Okay, so that's supposed to be the point. Okay, so to think of superpositions as classical coin tosses is to fail to see this counterintuitive aspect that Schrodinger was trying to highlight to us. Okay, that quantum superpositions are not randomness from ignorance. And this is why I want to say that there are many analogies that are often used for qubits or superpositions that don't work. That qubits are yes or no or maybe, that qubits are coin tosses, qubits are spinning coins, or like the worst one that I've heard is So there was this one time during a quantum mechanics module, we were supposed to do an explainer video on like different concepts in quantum mechanics. And one particular group, apparently, they try to explain what a wave function or superposition is by saying that it's like finding out whether a girl likes you. Okay, this is not the way that it works, because as you guys probably have experienced before, some of you, too often the measurement result is pre-established. Whether the girl likes you or not has always been the case, and you will just find out. Of course, you could ask her in a very bad way to like then skew that when she actually originally liked you, and because you made a very bad measurement, you cause it that they don't like you anymore. Okay, totally possible. Okay, but my point here is that more often than not in these situations, the answers or the outcomes are pre-established. Okay, and so they don't ultimately work. Some of them don't work at all. Okay, right. So quantum systems at bottom, quantum systems ultimately do not have a genuine classical analogy, even for just a single qubit. When we're not even talking about like entangled situations, we already have very strange stuff going on. Okay. All right. Next thing I want to clarify is whether we can say plus and okay. So we have kind of introduced ourselves to these guys and this guy. Okay, look at this guy. He has like all this crazy stuff going on with the square root 2 and whatever, right? Okay, can we say something like plus and minus are superpositions, 0 and 1 are not? Okay, so when I say something like that, it really sounds very sus, and you guys are probably thinking that probably not lah. Okay, let me explain why. Okay, it's because there are only such things as superpositions or bases. Unless you tell me what bases you're using, you can't tell me whether something is a superposition or not. Okay, so there are no such thing as superpositions, full stop. Yeah, okay, there's only superpositions of some given base. Okay, and here's the interesting thing: just as plus and minus are superpositions of 0 and 1, 0 and 1 are actually superpositions of plus and minus. Okay, later we will verify this. And also notice that plus and minus are an orthonormal basis. Okay, so at this point, let me just kind of scooch over and show you guys and verify this. Okay, so what we want to verify now is that the zero and not only is plus and minus superposition of 0 and 1, but 0 and 1 are superpositions of plus and minus. Okay, and so this is what we want to prove over here. Okay, so let's try to do that. Okay, so let's just use this side first. Okay. So we expand it, right? So what's plus? Plus is basically just this. This is your plus. And then after that, we have the minus. Minus is this, right? Okay, so you guys can already notice this will cancel out, right? So what we'll have is actually square root 2 taking out the factors, and then there's 2 of these guys. So it's 2, and we have this. So we have proven this guy, right? Okay, the next one is almost too trivial to do it. Let me just kind of patronize you guys a bit. Okay, it's the exact same thing as this scenario over here. The only difference is that instead of plus here, we have a minus, right? Okay, which just basically means this. Okay, so this gets cancelled out with this, and we are left with square root 2, 2, and we have this. Okay, simple enough. So we have shown that these guys are actually superpositions to each other. So we can't say this crazy thing like, oh, 0 and 1 are not superpositions. Okay, remember that whatever we do, when we talk about superpositions, we need to mention the base that we're using. Okay. All right, next. So whenever a quantum MLM tries to sell you something and says that something is in the superposition, ask them what base. Okay. All right, let's move on. Okay, so let's verify that this is an orthonormal basis. And how do we verify there's an orthonormal basis? The first part we need to verify is that the inner product of these two guys is 0, and that the norm of these guys are, okay, that's confusing. Okay, but you guys get it, right? the norm of these two guys are 1. Okay, and it's quite obvious. Let me just show you guys. So the inner product of these two boys is, okay, the bra, it will be like that, the conjugate, and then you transpose it, and the cat will be as such. Okay, but of course, because these are real, the conjugate actually doesn't do anything. And so you have this 1, 1, minus 1, so it's 0, 0. Okay. How about this guy? What's the norm of this guy? The norm of this guy is just basically you take each of these elements down here, or the square root 2 squared plus another one, square root 2 squared, right? And so what do we have? We just have like that. Okay. The same thing goes for the minus k. Okay. So we have shown that it's an orthonormal basis. All right, very good. Okay, let's go back. Okay, so that's why we now can write everything on a nice diagram called sometimes we can call it the polar circle. Okay, it's just a convenience. And notice that the plus and minus basis is just as valid a basis as 0 and 1. Okay, all right. So now that we have introduced these two guys, okay, we can now introduce the general arbitrary qubit. Okay, and that any qubit can be written as such. And this is the form. Okay, any qubit can be written like that. But if it's a unique qubit, then it has to be a unique set of A and B. Okay, and A and B here are complex numbers. Okay, there's also this other thing called phase factor, but for now I won't talk about it. But just note that if you have a unique set of A and B, you basically have a unique qubit on your hands. Okay, and so if you use the vector notation that we have been using so far, the vector representation, then we can write it as such, kind of quaint and cute. Okay, very good. So to kind of understand what we're working with here, we can now move on to acting on the qubit. Okay, so some of you guys might be still wondering like what exactly this general qubit thing is going on. Hopefully by acting on it, you would see how it goes. Okay. So any pure qubit, if I write it on the polar circle that we have just introduced, will be written as a kind of arrow that touches the circumference. And the reason why it touches the circumference is because of this a square plus b square equals to 1 situation. Okay, but some of you might be asking like, okay, why does this constraint hold? And why will the qubit always touch the circumference of the polar circle? Okay, and the answer to that has a lot to do with the Born rule, and we'll kind of look into this. Okay, so what is the Born rule? The Born rule is a principle that gives us the statistics of measurement results given a quantum state. Okay, so it just tells us what are the chances of getting these measurement results given some kind of quantum state that we are working with. Okay, by the way, this works beyond just qubits. It's a kind of across the board thing in quantum theory. So the Born rule can be written as such. Okay, let me just explain what's going on. So this symbol here is called phi, and this symbol here is called psi. Okay, so what this means is the probability of getting a phi outcome, an outcome phi, given that I am working with a quantum system psi. Okay, and the Born rule states that the way to find this is to have the absolute value squared of the inner product of phi and psi. Okay. All right. I hope this is okay so far. We're going to work with this, and you will see how it happens. Okay. There's also this other thing that because we are working with qubits and every measurement basis has two outcomes, 0 and 1, or plus and minus and stuff like that. The normalization for qubits, basically meaning that the sum of all the probabilities of all possible events must always equal to 1. Okay, follows like this. What is the normalization for Q-trit, a 3-level quantum system? Then you have 3 terms, right? Because there are 3 different kind of members in each basis in the Q-trit space. Okay, so likewise, if we're using a linear basis, it also works like that. Okay, so let's just do some following examples so that we kind of know what we're working with. Try to follow as I go through these guys. Okay, so here we are trying to find out the probability of getting a 0 result, a 0 outcome, given a arbitrary qubit psi, and also the probability of getting a 1 outcome. Okay, so let's write the arbitrary qubit. out. Okay, so let's find the first dude. So the bond rule states that you have to put the inner product of 0, the outcome, and psi, and after that you have to square the guy. Okay, so let's just expand this dude. There's 0, the 0 bra over here, and after that for the psi over here we have a plus 1. Okay. Okay, so let me just very, very explicitly show you what happens. Sorry, there should be a square. Okay. You get this and this will come together for the 0, 0. Meanwhile, for B, we have 0, and then we have 1 here. Okay, and so because these guys are, we have an orthonormal basis, right? So the orthonormality will give us 1 here, okay, and the orthogonality will give us 0 here, right? Okay, the inner product will be 0. And so what do we get at the end of the day is a squared. Okay, so the probability of getting a 0 outcome is this a squared thing. Okay, remember that this can be a complex number. Okay, and so by squaring it, then you get a real result. Okay, so for one side, it's almost too obvious at this point. The only difference you have is that this is 1, and then you are acting on this once more. And once again, this and this will go to 0, this and this will go to 1. And so what you just have is basically b squared. Okay, so notice that we have the normalization condition here, right? Equals to a squared plus b squared, which is equal to 1. Okay, I hope that makes sense. So this is why these boys A and B over here, okay, are often called probability amplitude. Okay, because they don't give you the probabilities right away. What you need to do is you need to square them. You square already, then after that you get the probability. So they just call this, I don't know what I call this, then you just call it probability amplitude. Because in respect to in honor of the wave function, which you can think of as amplitudes happening sometimes. Okay, so A and B are considered probability amplitudes, and hopefully from this situation you can see why that's the case. Okay, so let's do these guys. Okay, P plus given 0. Okay, so this means that if I have a quantum system that is in a 0 state, and I want to measure it along the lines of the linear basis, what is the chances of me getting a plus result? This is basically what this is referring to. Okay, all right. So let's just work it out. Okay, some of you might be able to already forecast the result, but let's just do it. Okay, so 0 here plus 1 here. This is the plus state. Okay, and then for the 0 state, we have 0 out here. Okay, and so once again, these two guys will go to 0. These two guys will go to 1, right? So what that ultimately means is that we'll just have one of these square roots down here, squared, okay, which is just half. Okay. Likewise, for the minor situation, it's exactly the same scenario. Sorry, this would be a 1. Okay, I'm solving for this thing now. So 0 minus 1 square root 1 down here. And then likewise, we have a half. Okay. So just take note that we can actually infer, now that we have these two guys, we can actually infer these two guys by using the law of total probability or using normalization. Okay, why? Because remember that this plus this, okay, because this is the same state, and these are members of a basis. Okay, these make up a basis, then this will equal to 1. Okay, so we have already found out this guy over here, so we can find out this guy, and so this guy will just be half. Likewise, the other guy here will also be half by the same principle. Okay, and this is why the plus cat and the minus cat are sometimes called unbiased superpositions of 0 and 1. Okay, because it's half-half, right? There's no bias to either result. Okay, I hope this is all clear to you guys. Okay, the last exercise for this part with regard to the bond rule is a little bit more slightly deeper in some ways. Okay, so we are going to look at this arbitrary qubit and we want to evaluate this. Okay, so we are dealing with two arbitrary qubits now. Okay, we are dealing with phi and psi. Okay, and I define phi as C using C and D. Okay, and we want to evaluate the probability of basically getting any possible result between one arbitrary outcome and one arbitrary system. What's the probability of these guys? And just evaluate it to the bottom and just double check that the end result has no imaginary component. Okay, so let's do that. It's going to take a little bit more time, but let's try. Okay, so what is phi going to be like? Phi is these two guys, but remember, because we are taking the brow of phi, what do we have to do? We have to put the complex conjugate, right? So actually you'll be C star, the 0 cat, plus D star, the 1 cat over here. And then for phi, it will be A 0 plus B 1. Okay. So then we just slowly expand. Okay, so the first two guys, this one, we get C star A 0 0 plus C star B 0 1 plus D star A 1 0 plus D star B 1 1. Okay, and you guys should know by now this goes to 0, this goes to 0, this goes to 1, this goes to 1. Okay, so at the bottom we have C star A plus D star B squared. Okay, so we evaluate this part. Okay, so we C star A plus D star B star, okay, and then after that, the repeat of that. Okay, and so this would just be C A star plus D B star, C star A plus D star B. Okay, and if you just evaluate this guy out, is C squared A squared plus D squared B squared, and then we have Z plus Z star. Okay, where Z is C A star and D star B. Okay, it's because of the cross terms. When you multiply this with this, and you multiply this with this, you get these two guys. Okay, and why is that important? Okay, is that just take note that when you have a scenario where you have a Z plus Z star, it's just two of the real component of Z. Okay, why? It's because Z is just the real part plus the imaginary part, and then Z star is just the real part minus the imaginary part. And so these guys cancel out. And you have two, the real part of Z. So this is obviously going to be real. This is going to be real. And we know that this is also real. Okay. So the probability of an arbitrary outcome to an arbitrary system is going to be real all the time. Okay. It's going to have no imaginary component. Why is that important? It's because there shouldn't be imaginary components to your probabilities. Okay. All right. So that is all for this part. I hope you guys are following. Okay. So I'm basically reaching the last part of the lecture. All right, so this is where we deal with a quantum operator. So the Born rule that we have just explored is dealing with measurements. Okay, and as for how qubits change over time, okay, rather than measurements, how they change, okay, has to do with quantum operators. So just as the physical entity, say spin particles, polarization of photons, and so on and so forth, are represented by states, okay? And these states are represented by vectors, okay? Likewise, the evolution of the above or things acting interactions of the above physical entities are represented by these things called operators, and then operators are represented by matrices. Okay, notice that if I choose a different representation, I will have a different kind of vector formula. Okay, and likewise, if I choose different representation for an operator, right, I'll have a different matrix. So you can't say that an operator is a one-to-one with a matrix. You always have to select a representation before we know what kind of matrix to use to represent the operator. Okay, so before we dive into a very important class of operators, let me introduce to you guys a very important mathematical tool in quantum theory. And this is the thing called Hermitian conjugate. Okay, so what's Hermitian conjugate? Let me explain. So remember that for a cat, if I want to conjugate transpose it into a bra, I need to kind of transpose it and then apply a complex conjugate on it like this, right? Okay, so likewise, this can also be applied to matrices. Okay, and this is called a Hermitian conjugate of a matrix. Okay, so for the qubit space, we have an operator, and let's choose this representation A, B, C, and D. Okay, so the Hermitian conjugate is denoted as this dagger thingy. Okay, this dagger thingy represents Hermitian conjugate, and what you basically do is you transpose the guy, and then you complex conjugate all the entries. Okay, so so as you can see here, I flip the C and the B, and then I apply the complex conjugate on everything. Okay, so just notice that this is what it means to have a Hermitian conjugate operator. It's the matrix parallel of a conjugate transpose. Okay, so there are a lot of different kind of operators that can be conceived, but not every single operator can be used in a quantum setting. Okay, there are only certain kinds that can be used in quantum setting, and these are usually called normal operators. But basically, it has to do with this thing called diagonalizability. Okay, but among the valid quantum operators that are out there, there's a very special class of these operators, and they are called unitary operators. And unitary operators govern or describe a very important thing, which is how quantum systems change over time, or how physicists usually will say how they evolve. So unitary operators describe the evolution of quantum systems. Okay, and we have already kind of met this word unitary, but let me kind of explain it in a deeper way for you guys. So just as there are physical entities that are represented by states and then states represented by certain vectors given some kind of choice, the physical entities, how they evolve and how they change will be described by unitary operators, which are then represented by unitary matrices. Okay. So for some of us, we might be already thinking like, okay, but how do I know whether a matrix is unitary, right? Okay, because if I know whether a matrix is unitary, then I know that I'm dealing with a evolution of a quantum state in some way. Okay, so then how do I check whether a matrix is unitary? We have already met the definition for a unitary matrix in the math lecture before. Okay, and it has something to do with conserving the inner product of two vectors. Okay, and so but unless you're willing to go and slowly, which is ridiculous, right? You go and slowly go and plug in every single vector's inner product to go and check whether it is conserved. Clearly, that's not going to be what you're going to do, right? What you want to do is to come up with a better way of testing. Okay, so how do we test? Okay, that is where we need to go to the drawing board. Okay, so we want to find a way to identify unitary matrices. Okay, and so let me just kind of reiterate that a unitary matrix is whatever conserves the inner product of two vectors. So what this means is that after I act on some kind of vectors like this, Okay, v1 prime and v2 prime are like the vectors after they have been acted on, or the states after they have been acted on by this operator. Okay, and I want it such that the inner product of v1 and v2, it basically remains unchanged after they have experienced the unitary operator. Okay, and by the way, this must apply to every v1 and v2. This is a very important condition. Okay, because you can have a unitary operator whereby it applies this thing holds for some given vectors, but not all. Okay, what makes it a unitary vector is that it applies to every single vector throughout the vector space, throughout the state space. Okay, so then how do we do that? Okay, so then let's just expand this part. Sorry, no, the other part. We expand this part down here. Okay, we have v1 prime 1 is actually the bra version of this. This guy is the bra version of this guy. But what's the bra version of that guy? Well, we have already kind of met the bra version in some sense. This is actually the bra version of v1 and then the Hermitian conjugate of u. Okay, just as you transpose the cat into a bra, when you transpose the u, you also will need to apply a dagger over. Okay, so if you want to verify that this is the case, you can just go and try a 2x2 scenario and you'll just find it very easily. Meanwhile, for this other dude over here, okay, it's just this guy. So we just add him in. Okay, and so this equality here, v1, sorry, v1, v2. Okay, and remember that we need to make this apply for all v1 and v2. This is for all. Okay. So for some of you who are a little bit more like, I don't know, you have the linear algebra spider senses tingling already, you'll know that the only guy that's gonna fulfill this is the identity here. Okay. And this, you can kind of think in terms of eigenvectors and eigenstates, but for now, I won't butcher the point. The point here is that if you want to apply it for all, then there's no way around it. This has to be the identity, okay? So basically, for something to be a unitary operator, it needs to fulfill this particular relationship. For C2, for the qubit space, okay, the identity is just this. Okay. All right. Very good. So I don't think are there any questions at this point? Okay, if not, I will deal with your questions later on. Okay, so very simply, the unitary operators can be represented by a unitary matrix fulfilling this situation. Okay, and so examples of unitary operators that you have already met in some ways are the Pauli matrices, and the identity is clearly a unitary operator. And this other thing called the Hadamard gate. Okay, so in order to kind of help you guys know what these unitary operators, how to play with these guys, I will then, why is there a double? Okay, that's weird. Okay, but anyway, I will try to verify that Y and H are unitary and that the following, and show you guys how to use these operators on some quantum states and then connect it with the Born rule. Okay, and that will basically be it for my lecture. Okay, I'll show you guys. So let's show that Y and H are in fact unitary. Okay, so what's Y? Y can be represented as such. Okay, so we want to show that it's unitary, right? So how to show that it's unitary? We need to show that Y dagger and Y equals to the identity. Okay, so let's first find Y dagger. It will be this thing transposed and then conjugated. So we transpose it, I minus I, we conjugate it, 0 minus I. So notice something strange is that Y and Y dagger are actually the same thing. Okay. this is not necessary for it to be unitary, but it just happens that both of the examples we're using today has this property. Okay, so y dagger y. Okay, we just put this together. So just slowly evaluate. So this one comes down, it's 0 plus I times negative I, which is just 1. This times down here is 0 times 0 plus 0 actually. This one is also 0 plus 0. This one is negative I times I plus 0. So that's 1. Okay, which is the identity. So we have shown that this is indeed unitary. Meanwhile, for the Hadamard gate, okay, the Hadamard gate looks like this. Okay, so what is the H dagger? Actually, it's actually itself lah. Okay. By the way, there are unitary operators that don't have this property. Okay, just take note. Okay, but let me just show you guys that these are in fact unitary. Okay, if you go and slowly do, this would be 2, this would be 0, this would be 0 also. After that, 2 here. So we have 1, 0, 0, 1, and that's the identity. Very good. So we have verified that these guys are all unitary. Okay, so let me just show you guys now the application of operators on these states. So the first one is the action of the Z polar matrix on the plus state. Okay, so what's the Z? The Z one, you can represent it as such 1, -1, 0, 0, and then for the plus, it's this. So just show you guys this is Z, and this would be the plus cat. So when you act on this, you get a square root out here, 1 corresponds here, 1, and then after that -1. So what's this state? It's the minus state. Okay, so this gives us the minus state. How about x acting on the minus state? We have, so x can be denoted as such, and then the minus, it will be like that. Okay, this one's almost too obvious. You have the 1 up here, you have -1 up here, then you have 1 down here. Okay, so then what's this? This is negative minus state. Okay, all right. By the way, if you guys have read your notes in the math notes, you will encounter this thing called eigenvectors and eigenvalues. These and eigenvectors and eigenvalues are basically vectors of which the operator does not change, does not rotate. Okay, so basically you have a minus cat here, and you have a minus cat here, and all you have is a constant, a prefactor of minus. So this minus is actually a eigenvector of x. Okay, if you want me to explain what this means later, I can do that. Okay, but let me just show you this. Okay, so 0, this one's very, very easy. It's just 0, 1, okay, which equals to 1. Okay, very good. Okay, so the final thing that we want to go through for today is to find the probability of getting a 1, okay, after we have acted on a 0 state using an X operator. Okay, so just note that just divide this down here. Okay, so just note that when we are dealing with a 1 for just a 0 state, okay, we have 1, 0 according to the Bond rule, and this is just 0, right? Okay, but if we are dealing with something that has been acted on by the X operator, okay, this thing, what we will have is actually this X O that squared. And as you know, we have already solved this. So this part is actually 1, right? And as you guys know, this would just be 1. So notice the very big difference. after you have acted on with the operator, you have actually changed the statistics of the of your measurement. Okay, so that's what's the role of the quantum operator, what it does, or for unitary operators at least, is that it can you can change the statistics of what you're gonna get later on. Okay, for the measurement. Very good. Okay, let me just close. Okay, summary. Okay, so this is basically all that we have gone through. We have introduced the computational basis, the linear basis, and then we also talked to you guys about how do you describe the general qubit as a whole. Okay, and now that I introduced the normalization of qubits as a bit of a side note, these guys down here are things that apply even beyond the qubit scenario. Okay, these will carry over even in situations of like multiple and entangled qubits and stuff like that. Okay, more conceptual stuff. Know that the physical entities that we're dealing with are represented by states and then represented by vectors. Evolutions are going to be represented by operators and matrices. Don't forget, the unitary operators are a very special sort of operator that deals with how the quantum system changes. Quantum states must be normalized. Your probabilities must add to 1. Once you see that your probability adds to something above 1, then go and check your working. Okay. Classical randomness by ignorance is very different from quantum superposition according to standard quantum theory. Okay, so there are certain questions that I have left unanswered intentionally. Okay, the first thing is, what do qubits and quantum operators physically look like, right? And what about multiple qubits? These are things that we'll be dealing with today. So after me, Lynn will be going through quantum optics stuff, okay? And then after that, I think Bengi will be talking about multiple qubits when you have entanglement and then the freaky teleportation stuff. Okay, how do these things translate to the lab? And how can they be applied will be dealt with, I think, in the further days where we talk about cryptography, quantum computing, and stuff like that. Okay, and so deeper foundational questions like what is the significance of this intrinsic randomness stuff? What does this all mean, quote unquote? Okay, these are things that I have left unanswered. Okay, but these are worth exploring as well. Okay, that is it. So Angelina, how you want to do this?